All right, so today, we're going to take a look at our next unit, which is circuit. Just kind of give us an idea as to where we are. I know this year we ended up having a healthy amount of snow days or winter weather days of some kind. Depending on how things go, especially for those that are seniors, this may or may not be our last unit. There's kind of a little small unit we do at the end that's a bunch of select little topics within light, sound, and waves and things like that. I'm hoping that we have the opportunity to get to that. But point being, this is kind of our last really big unit that we do because that one is just a couple select topics right at the end. So you can kind of do the math. We're going to be in this unit for a while too. Okay, we have a lot of stuff within circuits that we're going to talk about. And today, just to kind of set the stage, we're going to talk about kind of the basics as to what we're going to do and all the different things circuits related. Okay? Now, part of the reason why I like this unit is because this is kind of one of the areas where we've had a lot of technological advances. We're going to take a look from a very specific standpoint from the physics side and understand that even in the roughly month or so that we're going to spend in this unit, we're barely going to scratch the surface of all the things that we could do circuitry related. We're still going to do a decent amount of depth of things, but you could take an entire year's worth of collegiate level courses and still not cover everything that we would need to cover. So keep that in mind. Okay? So in our daily lives, and we certainly rely on, at this point, a lot of electric devices. Okay? Most of the ones that we're going to talk about in this unit, 99% of it is going to be the battery-powered objects. And we'll see why in a minute, but we're going to specifically focus on battery-powered objects. A lot of the same rules apply to things that are not battery-powered, but the rules are a little bit different to that. And again, if we had all the time that we needed, we'd have an opportunity to properly address that as well. Okay, so if we're going to talk about battery-powered objects, we need to start at the source. We actually need to understand a little bit about what exactly does a battery do. Okay? Now, I hope that you would understand by now that a battery, inside of it, there's a chemical reaction that occurs between different types of chemicals. It depends on the battery type. But the net result of it ultimately is, okay, that we are going to generate a whole bunch of excess electrons. And the goal for that battery is, within whatever it gets plugged into, is to be able to push these electrons through the circuit, okay, from one terminal to the next, okay, from the cathode to the anode. Now, using the prefixes that I know you've probably heard before, cathode, is that going to be the positive terminal or negative terminal? It is the positive terminal, in the same way that a cation is a positive ion. The cathode is the positive terminal to the battery. And, a lot like the anion is the negative ion, an anode is the negative terminal to that battery. Now, in order for a battery to have power, or what we would call power, there has to be a difference in charge between the two terminals. Okay? Most specifically in physics land, we call that an electric potential difference. Effectively, we have a difference in the buildup of charge between those two terminals. So what happens when a battery goes flat? For the most part, there's not much of a difference between the charges built up on the two terminals of the battery. Now, there's a whole bunch of terms that we could use for this. One of them is the electric potential difference. And in some physics textbooks, you'll see that written as an electromotive force, or EMF, that would exist between them. There's also a third and final term, and this is what people typically use and misuse when talking about this. That is voltage. What is voltage? Kicking it back to what our formative was there talking about that. Okay? It is quite literally the push that we're going to have to push charge through the circuit, as we're going to find out on our next slide. So, okay, in your typical batteries, okay, I'm talking more about like AA, AAA. I know that 9 volts and car batteries and things like they can look a little bit different. But I bet most of you have probably not seen a cross section of one of these batteries. Okay? I'm not asking you to memorize this. That's why it's not in your notes per se, but at least I want you to have a general understanding of what's going on. Okay, so if we were to take a cross section of, let's say, a AA battery, what we'd see is we have the positive terminal. The positive terminal is the one that always kind of has a little nub on the side of it. Okay? And that metal cap, where the nub is attached to a carbon rod. That rod, throughout the entire battery, okay, maintains what we will call kind of that positive terminal because of the chemical reaction that's going on within it. And then, mixed throughout, and depending on the type of battery, there's various different chemicals that are there. And we usually have typically 2 chemicals that are in that are going to react. And it is the job of that carbon rod that's in that battery to maintain that overall positive charge. Okay? So, in those specific batteries, AA's, AAA's, C cells, and D cells, the chemical reaction maintains a potential difference of 1.5 volts. Okay? This means, as we can see by the definition of a volt below, okay, that 1.5 joules of energy are required to move 1 coulomb of charge through a circuit using this battery. Now, ultimately, okay, what is the voltage? It's kind of a measure of the amount of energy that this battery is going to have to push charge through that circuit. And when it no longer has that energy to push, then there's not going to be electrons moving throughout the circuit, and we're not going to have what we need to operate. Okay? So yes, that is the textbook definition of a volt. It is 1 joule per coulomb. And something that I want you to become well versed in. You will hear these terms interchangeably used. Potential difference and voltage are the same thing. So if a battery maintains a potential difference of 9 volts, the voltage is 9 volts. Okay, and vice versa. And we will use those interchangeably. But in terms of trying to understand what is voltage, it is a way of quantifying the amount of push that we have to push that charge through the circuit. Okay, next concept. So kind of in your brain period, next paragraph. The battery creates an electric field within the wires once it's connected to some sort of circuit. That electric field exerts a force on the free-floating electrons within that circuit, and they respond to that electric field by moving. That movement of charge is the electric current. Now, when it comes to current, and I'll kind of come to some of these other bits in our slides in a second, sometimes the analogy is done using water. Okay? If you were to say, or let's say we were to try to quantify, what is the current of a river? What would we be actually trying to find? How would you measure the current of a river? Right?
Liters per second.
Okay, so a volume of water per second. I'm assuming you're standing at some point on it, and you're just going to try to measure the volume of water passing. Okay? That's really what we're doing with the current of a river. It would be the exact same thing as the current in a circuit. Okay? If somehow you were to be able to stand next to a certain point on that circuit to measure the quantity of charge, Q, passing that point per unit time, per second, that's what current is. So if we knew, okay, I'm going to stand right here, or we're going to measure right at this point in the circuit, and we know that there are 4 million electrons that pass here per second, okay, we can figure out the quantity of charge, okay, per unit time, to figure out what the current is. Now, there's a problem with using the letter C as a variable for current. And the problem is we actually use the letter C for something else, circuitry related. And that is capacitance, something that I wish we could spend a little bit more time to talk about. So we can't use the letter C. So we came up with the next best option, I. Yes, clearly, that's the best option. So current, we use the variable I to represent that. The units sure, it would be a derived unit because we have quantity of charge per unit of time, so coulombs per second is one way to express it, but the most common way is to express that as an ampere or an amp. So it's very elementary, but I use it every time I kind of get back to it. Okay, how do we remember it? CIA, current, the value, is represented by the variable I with units of amps, which is often abbreviated just simply as a capital letter A. Now, in a more elementary sense to what we have, I hope you understand there are two different types of current. We have direct current and we have alternating current. Now, if the charges move around the circuit following the same path, all going the same direction at all times, we call that a direct current. So the flow is constantly traveling in one direction. We get that for anything that is battery powered. Because once we have a battery or multiple batteries put in a certain way into a circuit, why we can't have batteries flipped around and other things, so once we have them the correct way in, it's all going to push the charge the same direction and keep pushing charge that same direction. So circuits that are set up to be battery powered, okay, are there to kind of help push all that charge in one direction. And years ago, well before either you and I were around, okay, when electricity was first started pumped through homes, it was done the same way, when everything followed one path and flowing in the same direction. But come to find out, that is a very inefficient way of having energy flow through your house. So think about this. If we had direct current in our homes, that would quite literally mean, let's say everybody in this room, in their house, you get your energy from the Lake Anna power station. We get a certain amount of it in the Northern Virginia area. I just don't know specifically as to where everybody's house is, what percentage of that power comes from where. But let's say that we all did. What that would literally mean is, at some point, the electrons in the wiring in your house had to come from all the way there to your house. As we would come to find out, there is a lot of inefficiency with trying to send power at a large scale over large distances. So we came up with a different system. Instead of the direct current, okay, anything that you plug into an outlet is going to use alternating current. Because ultimately, we're trying to harness the energy of this moving charge within our circuitry. So what are we then going to do for alternating current is, well, we're not going to try to have everything move large distances. We'll actually have it move very short distances. Okay? Because everything in that circuit is going to already have some charge in it. Okay? So what do we have to do? Well, we're going to kind of push it and pull it, push it and pull it, and kind of go back and forth, and just have them, not necessarily vibrating, but just kind of very quickly kind of moving back and forth. And that when you then plug into that, we're able to harness the moving energy of that charge for whatever it is that we plug in. Okay? So anything that you plug in into your house is going to get alternating current. Now, we have devices, we're not to the discussion yet, that are able to transform alternating current to direct current. Because obviously at some point, like for your phone, you need to recharge your battery. So we need to have a way of getting from one to the other. That's okay, we have those things in place. But just understand in the most basic sense, battery powered things are going to be direct current, and things that we plug into the wall, alternating current. Now, when discussing current and the direction of travel, it is customary to use the flow of positive charges when indicating the direction of current flow. I want you to read that statement again and tell me why you think it's wrong, even though it's true. Protons don't move. We've just stressed out a whole bunch in our last unit. So why is it that when we discuss electric circuits that we use the flow of positive charges when indicating the direction of current flow? Truth be told, we didn't know. When we first started to understand what was going on with circuits, we knew that there was moving charge. We just didn't know which one. Was it positive charge that was moving? Was it negative charge that was moving? Well, we guessed and we got it wrong. Okay? We now understand that things are a little bit different. We know that it is the movement of negative charge throughout the circuit. It's the electrons that are actually what's moving back and forth within there. But, and even to today, electrical engineers will still diagram what we call conventional current. Which I'm going to kind of add one little thing to what's on that slide. It is what I will call the theoretical movement of positive charge throughout the circuit. We understand that things are a little bit different, and for the most part, the direction of that current flow doesn't matter for most things. Whether it travels one direction or the other, not terribly important for most things, especially for things that are in a direct current circuit. So, very quick diagram up there. We have a 1.5 potential difference battery wired to a light bulb in a very simple circuit, and there's a diagram showing the current flow. Is that conventional current flow or is that electron flow? It is conventional, okay? As we see, from the positive terminal out and around through the circuit back to the battery. Also, I want you to be a little cautious about one thing, and it is a detail that can catch some people. Often when we talk about this, obviously we're talking about the movement of charge out and around the circuit. We're not necessarily talking about the movement of charge from within the battery. Because I want you to see this. Can you put your eyes on the board for a second? If we're diagramming conventional current flow, think of it this way. Around the circuit, positive terminal to the negative terminal. It is not positive terminal to negative terminal. Does everybody see that? Okay? So typically we're talking about what's going out and around the circuit, not through the battery itself. All right. Period. New paragraph. Okay, so we now have voltage or potential difference. We have current. We have another term that is called resistance that we need to familiarize ourselves with. Okay? The amount of current that flows through a circuit not only depends on the potential difference, but also the amount of resistance encountered by the charge. Resistance has units of ohms. Everybody say that, please. Ohms. Ohms. And we use the Greek letter omega to represent that when we get you its units. So you will not write out OHMS. Okay, you will write out the omega that is there. Okay? When we hand draw it, I don't know. Mine just kind of usually looks like this. That's just kind of how it is. So that is resistance. And as you can imagine, it is the resistance to the charge moving around the circuit itself. Okay, a couple of factors that influence resistance. Okay, resistance depends on the type of conductive material. Let's start with that. Okay, you can have a conductor, something that allows electric charge to move through it very easily, that's not going to resist charge moving through it. You can have an insulator, which is something that does not allow electric charge to move through it easily. Okay? That would certainly increase the amount of resistance that we have. Which is why wiring, pretty much at every single point, there is a conductor in the center surrounded by an insulator around the outside so it doesn't allow charge to leave the wire. Because it all stays within that point. Okay? But even within conductors, if you have a wire that's made out of copper, which is what most of your wiring in your house is made out of, that has a certain type of conductivity that allows charge to move through it. But that copper would be different than aluminum, which would be different than other metals too. So there's some variability depending on what the material is actually made out of. The next thing is the diameter of the conductor. And I'm going to kick it back to a water analogy for a second. I want you to imagine for a moment, not talking about electric charge, talking about water pipes. If we had a water pipe that was a very small diameter pipe versus a very large diameter pipe, which one would allow water to flow through it easier? The larger pipe. It's going to allow a larger volume of water through with less resistance. The same concept applies to electrical conductors. The thicker the gauge of the wiring, or whatever it is that we have, the less resistance it's going to encounter. The converse to that is also true. The smaller the diameter of the wire, we are restricting, we are adding resistance to the movement of charge throughout that circuit. Okay? The last factor to this is the length of the conductor. Okay? Even if it was the same diameter, if we try to send something through about, I don't know, 6 inches of wire versus 6 miles of wire, there's going to be a big difference in the amount of resistance because of how long we're trying to get that charge to move. Okay? So the resistance R, capital R, measured in ohms, of a piece of material of length L, cross-sectional area A, and resistivity given by, I'll be honest, I reframe this a little bit different. Resistance equals rho, which is what that funky little P looks like. It is the Greek letter rho, times the length, all divided by the cross-sectional area, represented by A. Now, let's talk about what he says R. R is resistance measured in ohms. Rho, which is the P with the kind of a funky little tail thing looking on the front, that is a given per type of material. So if we are using aluminum wire, I would give you a resistivity value for aluminum that we would have to use. If we're using copper wiring, we'd have a different value for that. The length is quite simply the length as expressed in meters. Okay, so that piece of it, not terribly difficult. Cross-sectional area. Since the wiring that we use for this, if you want to think of it this way, it's just a very, very long, very, very thin cylinder. If we take the cross-section of a cylinder, what geometric shape is that? It's a circle. So can we figure out the cross-sectional area of a circle? Yeah, that's going to be pretty easy. That's just the pi r squared. I know that that's down here on your notes, but just understand that sometimes we might be saying, okay, this gauge wire has a radius of, 2 millimeters. It's a pretty thick gauge wire, but just you kind of get the point. And we would then have to calculate what the cross-sectional area would be. All right, almost there. Okay, a couple of quick things. Okay, starting with Ohm's law. Okay, I know you do not have this imagery in your notes, but it's very simple. I actually even write Ohm's law a little bit differently as the base version of it, but this one also applies. I learned it as V equals I times R. Your voltage or potential difference is equal to your current multiplied by your resistance. You can see that the image on the board clearly has just done a little bit of algebra. That's I equals V over R. However you want to memorize it is up to you. Okay? But I stands for current measured in amps. V stands for voltage, or what's the other term? Potential difference, good. Okay? And then R for resistance measured in ohms. Okay? So if we know any two of those three, certainly we can go ahead and find the third. And then lastly, down at the bottom, something that I know you've heard of is electric power. There are a couple of different ways to find it, but the main version is P equals V times I, where the power in watts is equal to your voltage in volts multiplied by your current in amps. That's the main version to do that. Okay, I have two more down below that I'll explain in a second. Know that power we have seen before. In our working power unit a long time ago. Believe it or not, power then also had the exact same units. And it was also expressed in watts. Now, electrical power and mechanical power are two different things, but they are measured with the same units. So great, Talbot, why do we have these two equations down here at the bottom? Because, okay, we have the potential where we might have to solve for things a little bit differently. Okay, sure, P equals VI, base equation. But what if we didn't have voltage? Do we still find power? Depends on the other stuff we have, but more than likely. What if we took V equals IR and plugged it into the base power equation? So V equals IR, so take the I times R, and we plug it in for V. That gives us I times R, or I squared R. Or what if we didn't have current? Can we plug in V over R into that equation? Yeah. Okay. So that would be V times V over R, which would give us V squared over R. Now, you can memorize those two base equations as well, or you can treat everything as a two-step process. So you might have to go back and use Ohm's law and then get to electric power. All right. here's what I'd like for you to do. I'm going to give you a second. I would like for you to complete sample A and sample B. They're very simple and very straightforward, but just go ahead, take about a minute or two. Let's complete those, and then we'll talk about our responses in just a second. Okay, so let's go ahead and check in on sample A. Let's be real, A and B, this is not complex stuff here, okay? This is a pretty simple calculation for us to do. Just be mindful of our details. I equals V over R, 9 volts over 100 ohms. To give us 0.09 amps. We all agree with that? I will just say one thing I'm going to add while we're here, okay? I would put that 0.09 capital A, okay? That is the way in which we will abbreviate the amps. Sure, it is called amps, that's what it is, and sometimes it's listed out as such. But the more common thing to do is to truncate that to just simply the capital A. All right, sample B, okay? P equals V times I, okay, pretty straightforward problem. 120 volts multiplied by 1.5 amps, okay, to give us the 180 watts. We all agree with this? Yes, and in the same way we did with mechanical power, okay, and kind of the same thing here, I would just leave that as the capital W, and again, it's not wrong, it's just that that's how we will do that in the shorthand way of our units for that problem. Okay, all right, before we go on to what's next, just real quick, with Ohm's law and electric power, they are simple calculations. We have to check to make sure things are in their proper SI units. These problems, everything was already set up that way. But sometimes with circuits, we're either talking about the very large or the very small, so we're going to see some other units, other ways of having metric prefixes here. So just kind of keep that in the back of your brain. Make sure we're in our proper SI units. Okay. So here's what I'd like for us to do. Let's see. We got C, D, E, and that's it. Okay? So I would like for you to go ahead and do sample C. Take a couple minutes. Okay? You got sample C. All right, and then a quick check-in with C. Okay? And then some of us are still working on this, but obviously, current, we're trying to find current. You're not going to be able to do Ohm's law or electric power to figure it out. When you see coulombs of charge or anything related to the actual charge, you're probably going to kick it back to this equation, where I equals Q over T, the quantity of charge, which this way was expressed as 720 coulombs in 16 hours. And Ryan, I know it's pretty easy, but how do we get from 16 hours to what we just have up on the board?
Multiply by 60 squared. Because on the 60 on the 16 minutes an hour.
Absolutely. So we got to go all the way down to seconds. So 16 hours multiplied by the 60 minutes multiplied by the 60 seconds, which would be the unit conversion to get us all the way down to seconds. And that's where we come up with the value of the 57,600, which gets us, I believe it was 0.0125, which was then round to 0.013 amps. Okay. Almost there. Okay. This one I actually like to do with you for a second. Okay? The last couple I've had some student volunteers come up. Let's take a look at what we have. A defibrillator is used during a heart attack to restore the heart to its normal beating pattern. A defibrillator passes 18 amps of current through the torso of a person in 20 milliseconds. How much charge moves during this time? So ultimately, we're trying to find what? The quantity of charge. Okay? But we don't have that information to start with. We do have a current, we do have a value of time. So what would the rearranged version of that be? If it's I equals Q over T, that would become what? Q equals I times T. Okay, well that part's pretty easy. Okay, so then we have 18 multiplied by the time, 20 milliseconds. Again, the lowercase m stands for milli. So how many decimal places does that have to move? 3 to the left, so 1, 2, 3, which would give us what? 0.020 seconds. Okay, so let's do a quick calculation of what that would be in terms of the quantity of charge. Yeah, be quick, please. Cole, what'd you get? 0.36 monkeys, bananas, gallons of milk. Good, coulombs, because we're talking about a quantity of charge. Okay, I'm glad you got that. Okay, now I want you to hear this clearly. I did not ask it here, but it could be asked. Following on the heels of electrostatics, if that is 0.36 coulombs, could we, not asked on this problem, but could we work backwards to figure out how many electrons that would be? What would we do? We divide by Q. Okay, we would take what we have here, divide by Q, and that would help us to figure out what we'd have in terms of the total number of electrons. It is possible, okay, I'm just saying that just that they are related. Okay, so some of that tenet of electrostatics might crop up again during our circuits unit. Okay, I think this is our last one. Yep, sample E. Okay, an aluminum high voltage power line has a cross-section area of 4.9 of 10 to the negative fourth meters squared. If the resistivity of aluminum is that, what is the resistance of 10 kilometers of this wire? Okay, so we're going to use the resistivity equation. Rho L all over cross-sectional area. Rho, again, is the resistivity. I guess I didn't say this earlier, but it is in units of ohm meters. So if you see that, that's our resistivity value. So 2.82 times 10 to the negative 8 is 2.82 E negative 8. Okay? Multiplied by the length. So we have 10 kilometers of wire, so we're going to put in a 10, and then we're all done, right? It does say kilometers, so what should we do? And that would be 10,000. Good. Close, close. All divided by the cross-sectional area, which is given to us in meters squared. That was very nice of this problem. Thank you, problem, okay, for giving it to us in those terms. Okay? Know that we could have been presented this differently. If we were given the radius of that wire, we would have to do the pi r squared to get the cross-sectional area. It was already given to us in meters squared, so we didn't have to do that.
Would you rather find the area before the problem or just plug it into the equation?
It's a good question. I'm fine either way. Okay? If you were to go ahead and kind of clarify what Alyssa's question is, like we would potentially calculate 4.9 e to the fourth or e to the negative fourth, or to literally in parentheses pi r squared and have all of that in parentheses, doesn't matter to me. Okay? Obviously, to kind of reduce the rounding error, you're going to be a little more accurate with doing the pi r squared in the substitution, and that would be more akin to what an AP physics, higher level physics would certainly be asking you to do. But in terms of just the number crunching piece of it, it's fine by me. Yes, when we do that, we don't have to here. We should be using that pi plus, okay, not 3.14. All right, let's calculate this, and then I'll come back to questions. You got an answer? Quick, please, go. Ziad, you got it?
Yeah.
What you got?
0.576 ohms.
Good, 0.576 ohms. Now I want to talk about this answer for just a second. I know we have nothing to base it off right now because we haven't really done any calculations. See, is that a lot of resistance? Is that a little? That's actually a very small amount of resistance. If you think about it, 10 kilometers, you know, it's not a short distance by any means. But it still is probably a healthy run of wire that we're only getting half an ohm of resistance. That is very generous considering what it's trying to do. Okay? We get a lot more resistance out of other conductors within other things, so it's actually pretty significant. Now, all of those factors come into play. The larger the cross-sectional area, which that's a pretty large cross-sectional area, all things considered, that leads to that fact. Power lines themselves, I don't know if you actually see what I'm looking, the cross-section is actually about like this. Okay? Almost softball size in terms of its total diameter across. Okay, so depending on the power lines, those lines can be very large, and for that reason. So, this is where we're going to stop for today. So let's talk about the things we're going to do for next class. Twofold. Okay? First, we're going to take out the Ohm's law and electric power practice. first one that you got. One of the things I'm going to highly stress with this, and this one is due for next class, please check the metric prefixes. Okay? You're going to see things like a kilovolt. No different than a kilometer in terms of a conversion. You think, what's the base unit? What do we have to convert it to? But there is a new one, flip to the back. And if my memory serves me correct, I believe it is number 14. You have seen little m before. Little m stands for what? Milli. So a millimeter, okay, little m, okay? But we see capital M here, which stands for something different. What does it stand for? Mega. Okay? What does mega mean? Yes, it's actually a very defined lot. Okay? And what is that very defined a lot? No, more than that. Million. Okay? But million. Okay? So if you were to have, let's say, 1 mega amp or a megavolt, okay? That is a million amps or a million volts. That would be a lot. But okay, that's what the mega stands for. So when you see the capital M, just kind of heads up with that. Okay? The other thing it's going to do is the very clear successor to Ohm's law and electric power part 1, and that is Ohm's law and electric power part 3. Okay? So those are going to be the two things that are due for next class. Any questions?